Morning, folks. How y'all doing? Doing okay? Gosh, where's everybody? Huh? Is there something going on I don't know about? Is it too early? Seriously? Is it going to be bad? Oh, okay. All right. Well, I want to do a few administrative things. So, hey, um, I sent y'all an email. How do y'all feel about that? Feel okay? I think that's probably better for y'all because in the end, we're going to be pushing toward to get your projects done. I'm sure that some of you will put off some of that till the very end. And everybody else sort of puts off tests till the very end too, right? So that'll sort of get rid of that last crunch. And we'll have your final exam be half cumulative. And that's largely going to come from previous quizzes. I'll take those questions and sort of change them a little bit, maybe change the numbers, maybe change the wording, sort of slightly different question, but still the same topic and idea. So that would be a good way for you to study for that final. And then also half of it will come from the last couple of chapters that we do. We don't have long left. Y'all realize that, right? There's, I think, 6 class days, or it's actually 7 including today. And one of those, April 25th, I'm going to be out of town. And what I'm going to try to do is have your quiz planned for that day. And I'll try to find out as soon as I can so that somebody else will have to come in and proctor that last quiz. But it'll just be the quiz on that day, half hour for the quiz. I'll let y'all know as soon as I can if that's going to be the case. All right? Are there any questions? Any news about anything? No? Oh, here they come. Oh, thank you. Whoa. We're going to, I'm also going to move the project due date back another day. So instead of, it'll be the next to last class day. Let's look at the calendar. Right now I have it due on April 30th. So let's move it back to May 2nd. I think that's right. So this is April. The last class day is the 8th. On the 7th, we'll sort of have a wrap-up reviewing for the final, all that jazz. And so we'll have the project due on Thursday, May 2nd. Thursday, May 2nd. I got that? Project's due on Thursday, May 2nd. So it was due on this Tuesday, but now it'll be due on the 2nd. Well, my birthday is May 27th, in case any of y'all wanted to get me a gift or whatever. Just send me a nice message. All right? Also, sort of our chapters, sort of forming up some new things here. I think we're on chapter 10 right now, and we might just do a portion of that, but then I want to skip down to geometric optics and cover just a little bit of light, reflection and refraction, and using mirrors and lenses. So likely that's what we'll do next, but I'm still sort of forming that up. All right. Just sort of recap what we did last time. See, we left off with electric fields. We sort of had several ideas. First of all, the concept of charges. Turn these lights off. The concept of charges. We said that charges had several different properties. We have 2 types of charge. What are the 2 types? What types? Right, positive charges and negative charges. Positive charges are made up individually of specific quantities. Those quantities are called protons. And then negative charges are made up of electrons. So charge has several properties, positive, negative. They're also, charge is conserved. That means you can't destroy charge, like you just can't make it disappear. Charge is quantized. That means that it comes in specific quantities. Right? And we gave that specific quantity, that's called the fundamental unit of charge. I gave y'all a number. You don't need to know that number. It'll be on your equation sheet, but you need to know that it exists. And that fundamental unit of charge is 1.6 times 10 to the something, negative 9. Yeah, I know, negative 19. Thank you, Jaslyn. 10 to the minus 19 coulombs, and that's the unit that we measure charge in. We also said that like charges, if I bring 2 positive charges within the vicinity of one another, what are they going to do? Are they going to be attracted or repelled? Repelled. So 2 positive charges would be repelled, and to a positive and a negative charge, on the other hand, would be sucked together. They're attracted to one another. And those electric forces are largely what acts in atoms when we have a positive nucleus and a negative electron, that they're bound in orbit by these electric forces, which can be very strong. There are a couple of different homework problems, which I just put up this morning, that deal with the magnitude of this. We also looked at Coulombs Law. Coulombs Law describes the magnitude of these forces. F was equal to K QQ over R squared. Very likely you'll have to apply Coulombs Law. Given two charges and the distance between them, what is the force acting on those two charges? All right. K, remember, is Coulomb's constant. That's a value. Again, you don't need to know the value, but you need to know that it exists, and it'll be on your equation sheet. Q are the two charges, and R is the distance between them. And it looks like the last thing that we talked about is that the electric field, and this electric field describes the force on a charged particle. And it's defined as, the electric field is defined as the force per unit charge. So if I have a charge that's in an electric field, and we usually draw electric fields with field lines like this. If I have a charge that's in an electric field, so I have this electric field that's generated in some way, and I bring a charge and put it right here, it's going to feel a force. Right. I want y'all to know that electric fields exist. We're not going to deal with them quantitatively, but they're fairly important. We talked about one application, or I showed y'all that video, that TED Talk, where they use electric fields to move charged particles within the body in an effort to slow or stop the growth of cancer cells. I think in the years to come that we'll probably see more applications of electric fields and medical uses. So I just want y'all to know that it exists, and that these electric fields describe the force that charged particles feel. All right? Follow me on that? Electric fields can get a little complicated, but I just want y'all to know sort of that basic understanding that they exist. They describe the force that charges feel. And there are a couple of homework problems sort of dealing with that as well. The next thing that's in a similar way to the electric field, it can get kind of complicated, but we're going to sort of take it from a more simplistic approach, is the idea of voltage or electric potential. These are largely interchangeable terms. So like, for example, when you're talking about electrical circuits, like a 9-volt battery, that's the voltage of the battery, you'll often use the term voltage. And then sometimes we'll also use the term electric potential. You should know that those are, well, they are identical. They're just synonyms of one another, voltage and electric potential. As I said, this is commonly seen on batteries. For example, you have a 9-volt battery or a 12-volt battery. The SI unit for this, for voltage, is the volt. And this has more basic SI units of 1 joule per coulomb. That's joule per coulomb. Do y'all remember what a joule was a measure of? We've seen that before a couple of chapters ago. What is a joule a measure of? It's similar to the calorie. Calorie is also a measure of this quantity. What's the joule a measure of? This is the SI unit part. It's energy, right? Joule is a measure of energy. And then, of course, coulomb is a measure of electricity, or more specifically, electrical charge. Right? So joule is energy, and coulomb is charge. So as a basic sort of fundamental understanding of voltage, it's a measure of the energy per unit charge. This is a measure of energy per charge. All right. Let's imagine that I have this positive charge. I have a positive charge here, right? And I bring another charge near to it. I bring a charge here, and I place it at position A. This is plus Q. And then I bring another charge over here, and I place it at position B, plus Q. Both of these have a certain amount of potential energy. That is their potential for motion. Potential energy is just the potential for motion. Remember we talked about this in terms of gravitational energy. So when I have an object like this chair, I can place it here, or I can place it up over my head. Where does it have more potential energy? Over my head or down low? Over your head, because if I drop it here, it has more potential for motion, right? Potential energy is just a measure of the potential for motion. And so what about these charges? Both of them have potential energy at position A and at position B, but which one has more potential for motion? That is, if I place a charge in position A or place a charge in position B, which one would move more? The one at A or the one at B? Nothing. B. And now it's not B. You want to think about your forces. Go back to Coulombs Law. And this is where there's a homework problem dealing with gravitational potential energy and electric potential energy, and this is sort of where they begin to be different. Remember Coulombs Law, F is equal to KQ over R squared. Which of those, A or B, feels a greater force on it? A or B, the charge at position A or the charge at position B? They're identical. They have the same charge, but the particle at A is a lot closer than the particle at B. So which one feels the greater force? A, because it's a lot closer. In fact, if it's twice as close, how much more is the force? 4 times. By the way, you could very much expect, I would expect actually a question like that, where I give you Coulombs Law, and you have a homework question like this, and if I change the distance, how does that affect the force? So if I halve the distance, that quadruples the force. Or if I double the distance, it's 1/4 the force. Or if I double the charge, what does that do to the force? It doubles the force. If I double one of the charges, it doubles the force. All right, so that sort of mathematical relationship I would expect to see on the test, on the quiz. All right, so the charge at position A, big or small force compared to B? Big force, right? Much bigger. Like the way it's drawn, maybe 9 times or so as big because it's about 1/3 the distance. So my force on particle A is big, and the force on particle B is small. So let me ask you again, which one of these particles, if I let them go, will have the greater potential for motion? A has the greater potential for motion because it has that bigger force. It's going to zoom away really quickly, but particle B is just going to zoom away kind of more slowly. So particle A has a greater potential for motion. You write that in words. Particle A because it feels a greater electric force. Has a greater potential for motion. That means that it has a greater potential energy. So its voltage is higher. Than particle B. All right, because voltage, remember, is just energy per charge. So if 2 charges, if one of them has more potential energy, more potential for motion, then it's going to have a larger voltage or a larger potential. Be careful because we sort of throw around these terms, potential and potential energy. While they're related, they're not the same. That potential describes the energy per unit charge, and potential energy describes the actual energy, or the potential for motion. Y'all clear on the difference between those two terms? Be careful as you're reading because they can get confusing at times. All right. I'm going to show you a couple little things that are just kind of fun. There's a lot of cool stuff that you can do with charges. I have a little experiment. Well, let me show you the clip first. I have a little audio clip. I'll play the clip for you. No, I'll go ahead and show this to you, and then I'll play you the clip. This is Scotch tape, right? No, Scotch tape. Do you know what makes it sticky? What is it that makes sticky things sticky? Have any idea? What is that? Right. It's basically electrical charges that you have positive and negative charges that are bound. Now, in a more complex way, there are glues and they're sort of made up of molecules. But the basic things that hold these sticky things together are electric forces between those molecules, either in the glue to the surface or whatever it is that it's sticking to. And so if I take two pieces of tape and I put them on a surface, and one piece of tape, you can already see how it's sort of attracted to my hand. That's because the tape is charged. We can do a little experiment here. I'm going to put a piece of tape, it's about 8 inches long, and then I'll do another piece of tape. Now there are electrons on the desk, and there are charges on the tape as well. So what happens if I rip the tape off of the desk? What will I get on the tape? What will it do to the electrons on the desk? Right, it's going to rip away those electrons from the desk because of those sort of intermolecular forces. It's going to rip away the electrons from the desk. So my two pieces of tape are going to be charged. So hopefully they'll be charged in the same way, likely, if you're taking them from the same material. And so when I try to bring them together, they're going to be repelled. You see how they're repelling one another? I'm trying to bring them closer and closer. You'll see that in the back? Oh, at some point they stick together because they transfer charges. I have a little clip I'm going to share with you to sort of talk about this. A little radio. So remember, like charges repel and opposite charges attract. And that's the reason, because when you rip the tape up off the desk, it rips away those negative charges, and they both become negatively charged. I don't need that. All right, let's look at an example here. There's a homework problem about this, and in your book they go into cathode ray tubes. Are you familiar with cathode ray tubes, what those are? Maybe, maybe not. You know, do you remember TVs like they used to be? Now all of your TVs are flat screen. But used to, you had your TV like this, and then the depth of the TV was about the same as the width. It came in this big box. That's called a cathode ray tube. And it makes some interesting applications of electric fields. I want to go through, and I want to work through a problem like you'll encounter in your homework. Well, let's look at cathode ray tubes. They look something like this. This is sort of a side view. So this is the front of your TV right here. It's a screen. It's a phosphorescent screen. That means that there are different chemicals in each pixel, and if you strike them with a charged particle, then they'll turn a particular color. So you have this big array of pixels, and you just want to strike them with charged particles to make them particular colors. So this is just the screen. And then it's sort of closed off in this big tube. And here you have this wire that you run a current through, and that wire will put off electrons. So electrons come out of here, and they go in this direction. And you want to direct these electrons along different paths to go onto the screen. And you want to direct them to go in a particular position on the screen. So if I were to look at the screen on the front, I have an array of pixels right here that are blue, red, green, whatever. If I want a blue pixel to be at that position, depending on what's on TV, I'm going to direct my electrons to that position on the screen. So you create this stream of electrons, and you want to put them into different positions. And the way they do this is kind of ingenious. And actually, this comes up in other things that are more modern, like in inkjet printers, which you'll see a homework problem like. They have a couple of plates here. See if I can draw in 3D. They have a plate here and a plate here. These are connected to an electric circuit, and they have charges on these plates. So like, for example, I'd have a positive charge here and a negative charge here, and it would generate an electric field between those plates. Remember, electric fields describe the force the charged particle feels. So if my charge came in between those two plates, what direction would it go? Would it go up or down? If it went through those plates, would it go up or down? Remember, opposite charges attract and like charges repel. So is it going to go up or down? It's going to go down because it'll be attracted to the positive charges on the bottom and repelled from the negative charges on the top. So if my charge went through this plate, it would go down, for example. And you can modulate the strength of the electric field between those two plates to make it go to a particular position. And then you have other plates. This is going to be a little more difficult to draw. So these would be for vertical adjustment of the electron beam. But then you can also have plates that are for horizontal adjustment. So instead of being like this, they're oriented like this. Let me see if I can draw that from the side. So I have a plate here, and then I have another plate behind it. All right, so if these two plates are like this, then these two plates are like this. And they're going to cause that beam of electrons to go side to side. Now, within this is we have this stream of electrons that is going back and forth. And the way we do that, I'm just going to go to a new screen. Let's do this as an example. Let's say that we have two plates. I have one plate that's positive, and I have one plate that's negative. All right. And at this position, I'm going to say that the difference in potential, that's going to be delta V. Let's say it's, I don't know, 12 volts. All right. I have a difference in potential of 12 volts. Now remember, voltage is energy per charge. Voltage is energy per charge. Let's say that I have a negative charge right here. This is going to be an electron, and it's right here. It's going to be repelled from the negative side, and so it's going to go towards the right side. It's going to go over here. I want to know with what velocity does it strike? What is the electron's velocity when it goes to this positive plate? Right. We're going to sort of dig up some stuff that we've done before. Over here, before the electron moves, it has potential energy. And then it converts all that potential energy as it races across these two plates to get to the positive side. What will that energy then become? You have this potential energy. What is it converted into? Kinetic energy, right. So that potential energy is converted into kinetic energy. So here it has potential energy. And then over here, when it races across that plate, it's going to have kinetic energy. Now, if you remember, back a few chapters ago, and it's on your equation sheet, but kinetic energy is 1/2 times the mass times the velocity squared. So if I can determine the amount of kinetic energy that this electron has when it races across these plates, then I can figure out its speed fairly simply. But remember, we're going to go back to our voltage. The voltage is just energy per unit charge. So I can take this and find the amount of energy. The energy is going to be voltage times charge. I just multiplied both sides by the charge, Q. So I can find that. It's going to be 12 volts times Q, which is 1.6 times 10 to the minus 19. That gives me 1.9 times 10 to the minus 18 joules. So that's the amount of potential energy that this electron has here, but it's also the amount of kinetic energy that it has when it races across that plate and converts all of that potential energy into kinetic energy. Remember, we had a similar problem before when we had dropped something. Say if I drop this from here down to the ground, I say it has a certain amount of potential energy here, and then I drop it, and I convert all that potential energy to kinetic energy, and so we could determine what was the speed of the object just before it hit the ground. I forget what chapter that was, but it was a few chapters ago. This is basically the same idea, except now instead of gravitational potential energy, we're dealing with electric potential energy. All right, so now that I know the amount of energy, I can find the speed. So I say 1.9 times 10 to the minus 18 joules is equal to 1/2. The mass of an electron, again, you don't need to know the number, but you need to know that it exists, and it's on your equation sheet. It's 9.11 times 10 to the minus 31 kilograms. That's the mass of an electron times v squared. And then I would divide both sides by 1/2. And then I would also take the square root of both sides. That gets, these cancel out, and the square root gets rid of that v squared, and I get a v here. It's going to be pretty big. Actually, these numbers aren't realistic, but we'll go with it nonetheless. No, that's reasonable. 2 times 10 to the 6 meters per second. 2 million meters per second. This is just a 12-volt potential difference. This is like your, your 12-volt battery in your car or whatever. 12-volt potential difference gives my electron 2 million meters per second. That's fast, right? You don't think that's fast? 2 million meters per second. All right. Let's look at other couple of things. I'll hold off for just a second. I want to define current. We might use current a little bit later. I'm uncertain whether we're going to use it, but I just want you to know what it is because we sort of encounter current a lot out and about, sort of in the world. Current is just a measure of the flow of electricity. If I have a wire, this is a wire. There are electrons in this wire, and they're all sort of moving along in their way at a certain velocity. And the current just says if I sit here at this particular point, how many charges are going to pass in a particular amount of time? And so how many charges pass a point in a given amount of time? In this case, our given time will be a second, because that's the SI unit. And the charges are measured in coulombs. So the unit for current, SI units, is going to equal 1 coulomb per second. Anybody know what the unit for current is? Starts with an A. Amps, right. So the unit for current is the amp, or the ampere. This is abbreviated amp, or it's abbreviated with a capital A. Usually I think this is the main abbreviation. Mathematically, we would describe this as I and it's just equal to the charge divided by the time. We might get a little bit into circuits. I'm not sure. I think that we probably are not. But I do want you to know just what current is, and that it's just the flow of charge per unit time. Let's work a quick example with that. Let's say that I have a current. My current is equal to, I don't know, 2 amps. In a wire with this current, how many electrons pass in 1 minute? How many electrons pass in 1 minute? There are a couple things that you'll need to do here. First of all, you just need to find the amount of charge that passes in 1 minute. And since I know that the current is charge per unit time, I would just multiply my current times my time in order to find that charge Q. But that doesn't tell you the number of electrons. That just tells you the coulombs of charge. So how do I determine, if I have so many coulombs of charge, how do I determine the amount or the number of electrons that have passed? Divide it by what? Right, by your fundamental unit of charge. So that's that 1.6 times 10 to the minus 19. Right, remember charge is quantized, and so if I have 2 electrons, I have 3.2 times 10 to the minus 19 coulombs. If I have 3 electrons, blah, 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 on and on. All right, so I'll just first find the charge Q. So we'll go with this definition. I is equal to Q over T. And so if I cross multiply, or if I multiply both sides by T rather, I get Q is equal to I times T. So that's 2 amps times 60 seconds. That's 120 coulombs. So that's the first part of the question. And now if I want to know the number of electrons in that, I would say 120 coulombs divided by 1.6 times 10 to the minus 19. And if you want to think about your units, the units for this, you could imagine them being coulombs per electron. That's the number of coulombs per electron. And then the coulombs cancel, and it leaves me with numbers of electrons. So that's 120 over 1.6. I get a 7.5 times 10 to the 20th. That's a 7 with 20 zeros after it. I don't even know that number. But this is the number of electrons. 7.5 times 10 to the 20th. All right. As I said, we might see currents again if we get back to circuits. Okay with this? Oh, comfortable? If I told you all my O Street jokes? O Street? Like, what's the worst thing about living on O Street? All right, well, what's the worst thing about living on O Street? What? You don't know. Anybody know? You have to go a whole block to pee. You get it? O Street, P Street. That was pretty good. My boy liked that one. All right. Let's look at conductors and insulators, and then I have a couple little demos I want to show you. When we're talking about electrical materials, there are 2 types of materials with regards to electricity. 2 types of materials. You should be able to identify them and be able to describe why they are what they are. Those 2 types are insulators and conductors. All right, insulators and conductors, when we're talking about electricity, you can have similar things when we're talking about thermal insulation and thermal conduction. And actually, they're very similar. The reason that they conduct either thermal energy or electrical energy. And the reason is because they have electrons that are within those materials that move around really easily. For conducting materials, and then in insulating materials, the electrons don't move around very easily. And that allows for the flow of electrical energy as well as the flow of thermal energy. All right, so for conductors, they have lots of electrons. This is conductors, lots of electrons. Free to move. So electricity flows freely. Y'all think of some good conductors? Water? Copper. Yeah, copper is a very good conductor. Water, if it has ions in it, is a decent conductor. Charged particles, most water does. Most metals are conductors. So mainly metals are conductors. Because of the way their electrons are set up, they're able to move freely within the metal, and that transfers the electrical energy. So this is most metals. I think practically all metals. And then insulators, these have no free electrons or very few free electrons. And few or no free electrons. And they don't allow electricity to flow. Any examples of insulators that you know of? There are lots of different insulators. Rubber is a very good insulator. Wood, most cloths, fiberglass, plastics, a lot of plastics. Paper is a very good insulator. So let's see, rubber, wood. And also notice that these are very good thermal insulators as well, and very much for the same reason. They don't have these electrons that are free to move around, so they can neither transfer electrical energy nor thermal energy. So rubber, wood, paper, etc. All right. There's some things you can do that are kind of fun. I'll show you. With insulators and conductors and sort of static electricity. Of course, you can do that thing. Did anybody try that? Do y'all have roommates or whatever? Did I tell y'all about the whole Chris Reeks incident? The carpet, rubbing your feet on the carpet and chucking them in the ear. Anybody try that? You did? No? Okay. Well, you should try it when you go home. But there are some other things that you can do too. The first thing is probably the coolest, I think. This is a piece of copper wire. It's suspended from a string. This is just like what you'd find in your house, actually. This came out of our house, actually. And I have a piece of PVC pipe. And then I have like an old sock. It's been washed. It hasn't been worn in a long time. An old wool sock. Right? And if I rub the sock on the PVC, what it does is the wool will deposit electric charges onto the PVC. And since the PVC, conductor or insulator? PVC pipe. It's a pretty good insulator, right? It's a plastic, basically. So it's a pretty good insulator. And so those charges will stay there. Like, it won't shock you or anything, but it has charges on it. Right? And then copper wire, conductor or insulator? It's a conductor. What do you think will happen if I bring the PVC pipe up close to the copper wire? Do you think it'll be attracted or repelled from the copper wire? Now, the copper wire is not charged. It has free electrons in it, but it's neutral, electrically neutral. So what will happen, you think? You think it'll be attracted? I'll say. Let's try it, okay, and then I'll show you what happens. All right, so I get this charged up. Oh, I'm not touching it. looks like it is attracted to it. Make it go the other way. Can y'all see that okay in the back? Yeah, it's moving. You don't see it moving? Yeah. Piece of copper wire. I should paint it like day glow or something. Can you think of a model by which it's being attracted? Like, why is it being attracted? Because there are no charges, right? There is no net charge on this. There is no net charge. Make it go the other way. Stop, come back. That was just rotating. It's just rotating. Yeah, no. There we go. So it takes a minute to turn it around, but now it's coming back around and going the other direction. It's kind of a cool thing. In the clip that I showed you listened to, he talked about induced charge, and that's what you're getting here. Is you're getting what's called an induced charge. You have this string, and there's this piece of copper on it. Now, there are charges all along this copper. There's positive charges, and then there's negative charges. Now, the positive charges are locked into place, but those negative charges can move around freely. And then I bring a piece of PVC pipe over close to it, and the PVC pipe has just negative charges. I have a big excess of negative charge. So what's going to happen in the copper wire? Remember, like charges repel and opposite charges attract. What's going to happen in the copper wire? Right, the negative charges, they're all going to get the heck out of there because they don't want to be around the other negative charges. So it'll look like this. Those negative charges are all going to race down to that end. And that's going to leave me a net negative charge on one end and a positive charge on the other end. This is called an induced charge because the whole object still has a net charge of 0, that it's neutrally charged still, but I've moved some of those charges to one end. And now I have a positive end and a negative with the negative PVC pipe, and so it's attracted to one another. So this is called an induced charge. All right. The object is still neutrally charged as a whole, but the distribution of the charge is such that it can be attracted to charged objects. To the PVC pipe, which is negatively charged. All right. Let's see, I have a couple of other things. These are kind of hard to show in here. It's kind of humid. And actually for the same reason as this, that when it's very humid, because water is a polar molecule, that is, water is electrically neutral. There are equal numbers of protons and electrons. But because it's polar, those charges are sort of distributed in a way, so it appears like it has a charge, like it has an induced charge, kind of like the copper wire. And so water in the atmosphere can carry away charges. We talked about that before, right? That you get shocked by your car when it's very humid or very dry? When it's very dry, because you don't have that humidity to carry away electrical charges. Let's try this. Here's a little piece of paper, a little confetti. The balloon. So I'll try the comb first. I never get to use a comb, but I tell my wife that I really like to carry a comb, but I don't have any hair really, so I don't really need a comb. But when I comb my hair, what happens to the comb? it picks up charges and it becomes negatively charged, very much like the PVC pipe. I should part my hair. And I can let it apart. Let's try this. It doesn't really work. All right, my hair's not long enough. Let's try it with this. Right. Right. It doesn't work though, unfortunately. It does usually, but not today. It's kind of humid. Let's try it with this. Right. Now, anytime you have an excess of charge, that humidity will cause to sort of carry it away. And so I might get an excess of charge on my comb, but by the time I bring it down to the paper, it's basically gone. That usually works a lot better than it did, but this might not work either. Let's try. Yeah, I got a few pieces that you probably can't see. Yeah, that's lame though. But usually they all jump up on there. I'm sorry. I'll try the balloon. This is supposed to be really cool. And then y'all are like, oh, wow. All right. Balloons hold charge really well, usually. We'll try it. In fact, if you have like a sweater on a dry winter day, you can actually stick a balloon to yourself and it'll stay on you because of the charge. Let's see if this works. No, it doesn't work at all. Sorry. All right. Well, let me show you what's supposed to happen. If I have these little slips of paper, they're all stacked on one another. You know, they have positive and negative charges. Positive, negative. Right? They're all neutrally charged. But if I have a balloon, and I bring it over to them, and the balloon has negative charges on it, it's also going to induce a charge on those slips of paper, which will attract them to the balloon. So I'll get these little slips of paper that will come and attach themselves to the balloon such that their charges are distributed like this, where the slips of paper would jump up and attach themselves to the balloon. Now, paper is a conductor or an insulator? It's an insulator, right. But you can still rearrange the molecules within them due to the electric forces and cause them to set up this induced type charge, where I just arrange the charges that are already there and cause them to be attracted to charged objects. Right. Again, that's called an induced charge. All right. We're going to look at magnetism now just a little bit. And some of the applications that we have for it. So give me just a second. Give me just a second. Sorry, guys. Just give me a moment. A computer problem. There we go. Oh, here we go. All right, I want to listen to this. This is an episode from Car Talk, and they just talk about the shock that you get when you come into your car. So it's relevant to what we've been talking about here. Now remember car talk? All right, we're going to do a little bit on magnetism. Just a few little things on magnetism. How things are magnetized and what magnets are made of. Magnetism. Permanent magnets occur because of the alignment of their magnetic domain. I'll draw a picture in just a second. Oh, there's a picture in your book, too. And magnetic fields are caused by moving charges. They're caused by moving charges. Magnetic fields are caused by moving charges. So if I have an atom, I have a positive nucleus, and it has these electrons that are swarming around it in all different directions, like that. I have these moving charges in an atom, right? Because I have the electrons orbiting around the nucleus. So every atom has like a little magnetic field that we can envision. So every atom has a magnetic field. I'll let that be the red arrow. We're going to let B be our magnetic field. That's the variable that we'll use. And similar to the electric field, the magnetic field is going to describe the magnetic force that something feels. So every atom has its own magnetic field. Every molecule has its own magnetic field. And when I have permanent magnets, we're going to describe the magnetic fields of those atoms as domains, magnetic domains. So I'm going to say this is our permanent magnet. I'm going to break it into little pieces, like that. These are like collections of atoms within the permanent magnet, like one of those bar magnets that you see. I'll bring some next time. These are like collections of atoms within the magnet. And each of them has a magnetic field. And so, for example, if this is a permanent magnet, the magnetic domain of this particular region of the magnet would be in that direction. And then in this particular region would be in that direction, like this, like this. They're all going to be pointed in the same direction, these magnetic domains. Again, the magnetic domain refers to this region. This is a magnetic domain. And it just refers to this collection of atoms or molecules, and their magnetic field all point in the same direction. Now, this is for a permanent magnet, so it has a magnetic field attached to it. Just common materials, all other materials, non-magnetic materials, look like this. These are non-magnetic. This is everything other than a permanent magnet. If I were to map out their magnetic domains, all right, I would have an arrow going in that direction, maybe an arrow going in that direction, like that. So you see all materials have magnetic fields, but in non-magnetic materials, that is materials where you can't measure their magnetic field, what's happening to those magnetic fields from the magnetic domains? What's happening? What's happening to all the vectors that I draw in here? They're changing directions, and then what happens when I add them all together? They cancel each other out, right? So you, for example, as you sit there, you have these magnetic fields that are in your body, but they're all in opposite directions. So they all are just sort of randomly oriented, and so they all cancel out. Now, permanent magnets are caused a particular way in nature and in the lab too. We create permanent magnets, or rather in nature permanent magnets are created when molten metals solidify or cool in the Earth's magnetic field. So you can go out and you can dig up magnetic materials in the Earth, mine them, or you can create them in the lab too. But basically, you have a volcano, and it spits out lava, and that lava flows down the side of the mountain. All right, and when it's doing this within the Earth's magnetic field. And what that causes, the Earth's magnetic field will cause the magnetic domains in the molten lava to orient in the same direction as the magnetic field. So for example, here, you would get a little section of this, and the magnetic domains would all add up to go in that direction. And then when it cools, it locks those atoms or molecules into place so that their magnetic domains are permanently aligned all in the same direction. And that's the same way that we create magnets in the lab too. You take a metal and you melt it, and then you submit it to a very high magnetic field, a very strong magnetic field, and then let it cool. And while it's cooling, those magnetic domains get locked into place. Just a few more minutes, guys. I know you are getting antsy, but just a couple more minutes. Permanent magnets are made of what we call ferromagnetic materials. And in ferromagnetic materials, call them FM, that's for ferromagnetic material, their domains are easily aligned. All right. So for example, if you ever made an electromagnet, let me show you a little clip. Well, we don't have time. I'll show you next time. But an electromagnet is when you take, say, like an iron bolt, and you wrap a piece of wire around it, and then you put a current through that iron bolt or through the wire, and that generates a magnetic field, and it makes that iron bolt become a magnet. All right. Or if you hold a permanent magnet up next to a paper clip, and you get this string of paper clips underneath, it's like each individual paper clip is becoming a magnet in and of itself. Those types of materials are called ferromagnetic, and it just means that their domains are easily aligned. It doesn't mean that their domains are always aligned, but that you can align them by applying an external magnetic field. I'm following what I'm saying? Yeah. Okay. All right. So permanent magnets are made of ferromagnetic materials, and that just means that their domains are easily aligned. A couple more things. I'll be done with this slide. But magnets have north and south poles. Have north and south poles. And like poles repel, and opposite poles attract. All right, we will pick back up with this. We're going to sort of go over some applications of magnets. All right, guys, I didn't bring your progress reports today. I'm sorry I forgot, but I'll bring them back soon. But they look good. If I'll have to go back through them. I don't recall that there were any issues, but if there were an issue, I'll send you an email this morning. But I'm pretty sure that there were no issues. But I'll take a look. So if you don't get an email from me, just assume that you got a 20 on it, and I'll return them on, what's today, Thursday? I'll return them next week. All right? Y'all have a good day. Thanks for hanging in there. I know it's hard to come back after spring break.